Hello everyone, my name is Xingyu Zheng, and I come from China. Today I will present the paper, an empirical study of the performance of code similarity in automatic programming PR2. And here are the contents. I'm sorry. The first part is introduction. In recent years, automated programming PR has become a hot research direction. APR consists of automatically finding a solution to software bugs without human intervention, due to the fact that debugging software failures is still a painful, time-confusing, and expensive process. Redundancy-based programming PR is fundamental to APR, and it is based on the hypothesis that code may evolve from existing code that comes from somewhere else. For instance, from the program under APR, when given a false localization result, APR2 is based on redundancy search. So search code blocks that are similar to the buggy code block in the current program. The patches generated from these code blocks are then validated to find the first correct patch that pass all test cases. And our study of code similarity works on the performance of APR2 takes SimFix, a state-of-the-art approach to design the experiment and analyze the results. We utilize two similarity metrics that capture synthetic messages, LCS and TFIDF in both patch generation stage and patch validation stage of the tool. Then we design and perform a series of experiments. The main goal of the experiment is to study how good the new similarity metrics are at improving the rank of the first correct patch in the third space. And the related work is as follows. Redundancy-based APR. The APR process can be divided into three stages: fault localization, patch generation, and patch validation. And the first part, fault localization, patch generation. In the fault localization stage, given a buggy program, APR tool identifies an ordered list of suspicious buggy blocks using approaches like in patch generation stage. The tool first searches for donor code blocks that are similar to the buggy code for each buggy location. Then compares the buggy code and the donor code to extract patches for each donor code block and get the search space of patches. In patch validation stage, the patches are tried one by one from the search space to find the first correct patch that pass all the test cases. The next is the empirical studies on APR. Chen define and set up a large-scale experiment based on four code similarity metrics that capture different similarities: LCS, TFIDF, Deckard, and Zhiqiu vector. This paper considers two cases: contextless and context aware. That is one-line buggy code and a multi-line buggy code, and performs the experiments. According to their rank statistic, all of the four similar metrics produce over 90% of the search space in both cases. At the same time, LCS and TFIDF can rank the correct patch higher than Deckard and the Zhiqiu vector in contextless cases. And the performance of the formation is close in context-aware case. And this research helps our work. And the next is the overall research methodology in my approach. And the overall workflow of our work is illustrated in the figure. For each buggy program, the first localization stage returns a list of buggy code block. Just a buggy based on their suspicious score. Then the APR2 searches similar code blocks in the program for the buggy blocks. The similarity between the candidate code block and the buggy code is expressed to be more than the threshold. The searched similar code blocks will be ranked based on the similarity matrix of the APR2. Here we apply LCS and TF. Here we apply LCS and TFIDF. And this step returns the list of ranked candidate code blocks. Patch is generated from the candidate compose the source space. And different from the original process that directly validated the patches one by one. When a patch is to be validated, we first calculate whether it is highly similar to the patches that have been validated to be incorrect. If so, we exclude this patch and verify the next one. Otherwise, we validate this patch and add it to the set of incorrect patches. When the correct patch is returned. And in the patch generation part, our research methodology is as follows. In the patch generation stage, when given a list of candidate code blocks, original tool will rank them based on the structure similarity and the name similarity. We first directly add LCS and TFIDF respectively to the original match in the collected experimental data. Next, we combine LCS and TFIDF. Execute the tool with and without name similarity and collect the data. We investigate the statistical data of the rank of the first correct patch and the time cost for each bug based on different settings and compare which condition the probe performs best. In the patch validation part, we leverage LCS to filter out those incorrect patches. Since very unvalidated incorrect patches are similar to validated incorrect patches and are not similar to the correct validated patch, we calculate the similarity scores between the next patch to be validated and the patches which have been validated and filter out those patches that are very similar to the incorrect patch. We investigate the statistics data of the rank of the first correct patch and the time cost, and then analyze the performance of the filtering matrix. Here are the similarity metrics mentioned before. First is Deckard structure similarity between abstract synthetic tree and a variable similarity and a method similarity. This indicates name similarity. The LCS and LTF indicates longest common sequence and term frequency and inverse document frequency. And the next part is the evolution. We have three research questions. The research question 1 is how do LCS and TFIDF perform in candidate ranking? And the research question 2 is how does LCS perform in incorrect patch filtering? And the last is what affects the performance of LCS and TFIDF? In this table, column origin denotes the ranking result of the original tool. And the column denotes the ranking result of the combination of LCS TFIDF with the tool. And the column T and C and NS means the ranking result of LCS, TFIDF, and the Deckard combination with. And from the table, we can see both LCS and TFIDF successfully improve the rank of the first correct patch in many cases. We calculate the mean crucial rank of each setting and see that the performance of the LCS and TFIDF both improve the MR by 10%. As shown in the next column, we replace the name similarities metric with the combination of LCS and TFIDF and execute the program. The result shows that in this setting, MR has an improvement of 26%. And next is research question 2. And in this table, Oh, I'm sorry. The time means time is in minutes. And in this table, the column rank O denotes the rank result of the original two, and the column rank F denotes the rank result with ranking with result with the incorrect patch filtering. Now we can see that the ranks of the first correct patch of the bugs are extremely improved, and the time cost is greatly reduced. 75% improves the average rank of the first correct patch, and the average time cost is improved by 55%, and the average reduction of research space is 68% for the bugs whose ranking results have changed. And the research question 3. What affects the performance of LCS and TFIDF? The 26 bugs can be divided into two groups according to the rank of the true buggy block. On the one hand, for those bugs that the true buggy block is ranked first, the rank of the first correct patch improved when combining LCS and TFIDF with the original two, but filtering correct patches did not contribute to a higher ranking. On the other hand, on those bugs where the true buggy block is not ranked first, the source space was currently reduced by leveraging LCS and LCS to filter out incorrect patches. But leveraging LCS and TFIDF in ranking candidate blocks did not work on these bugs. Thus, the result of force localization and the size of source space greatly influence the performance of LCS and TFIDF. And here are two case analyses. First is long 27. For the bug long 27, the correct patch is a replacement of an if statement. Combining LCS and TFIDF and excluding name similarity improve the rank of the correct patch from 7 to 1 for this bug. If we do not exclude the name similarity, the rank is 4. According to the buggy code list, the true buggy code is ranked first, and this means all patches in source space are generated for this block. The original approach ranks the candidate block that contains the correct patch at 6, but the best setting ranks it at second. The tool does not extract any patch from the most similar block because it is equal to the buggy block. So the best setting successfully ranks the correct patch generated from the true candidate block first. Now, as shown in this listing, the first candidate is ranked first at setting 4, mentioned before, and the true candidate is ranked first in setting 5. This is because the first candidate block shares more variable and method names with the buggy code block than the true candidate. This leads to a low rank of the correct block. However, the correct patch is most similar to the buggy code when treating code block as a sequence of characters or tokens with LCS and TFIDF. So in this case, including all similarity metrics contributes to a worse result. And here is the second case. For the bug mass 57, the correct patch is to replace int with double. This modification is too small. Utilize LCS successfully improve the rank of the correct patch from 112 to 39, and the time cost is reduced from 5 to 3 minutes. We present the buggy code block to incorrect patches in this case. The two incorrect patches are extremely similar in character level. The approach generates a large number of patches like this. Filtering out these patches can greatly reduce the source space and greatly accelerate the repairing process. And as mentioned before, we initially set the filtering threshold to 0.9. However, the APR tool failed to repair this bug because the correct patch was identified as incorrect and filtered out before validating. This is because the patch is insert space are highly similar to each other due to the small size of the repair. We finally fixed the buggy code when the threshold was adjusted to 0.97. Good news is that although the threshold is really high, LCS still filters out 65 great patches for this bug. That's a conclusion. To rank the first correct patch higher in the search space and reduce time cost, we apply two similarity metrics, LCS and TFIDF in candidate code block ranking and incorrect patch filtering. We analyze the experimental results and get the following conclusion. First, in candidate code block ranking phase, combining LCS and TFIDF and excluding name similarity using SimFix from best and improve the MR by 26%. Next, in patch filtering stage, applying LCS to calculate the similarity between the next verified patch and the set of validated patches can greatly prevent incorrect patches from being verified. The method reduce first space of patches by an average of 68%, time cost by 56%. And that's all. Any questions?